And now I will introduce Elliot. So this is Elliot Kienzle, who studies geometry at UC Berkeley, and who is no stranger to the seminar, or the Discord for that matter, with many wonderful posts. And Elliot has presented a show and ask actually in the past, so this may seem, he may seem familiar. But Elliot produces extremely imaginative illustrations, and will tell us about manifesting mathematical worlds in digital art. So take it away.
Absolutely. So I want to tell you all about my project, and projecting my project down into a free word phrase. Closest thing to that is manifesting mathematical worlds. I'm going to do this in digital art because that's the medium that I use. And I want to start by introducing myself. Like I said, I like to draw mathematical worlds. And here is one such example of one of those worlds. This is a drawing of various different types of quantum field theory and how they relate to each other, imagined as a fantastical tree. Now, I'm going to get into much more detail on this later, so don't worry, but I'm bringing this up now because it's very exemplary of the sort of things I'm trying to go for. Like, what are my goals in making something? First, I'm generally trying to represent fairly high-level abstract mathematical concepts, and I'm trying to meaningfully communicate the mathematical content around the way. I want this to have some pedagogical value. But at the same time, I want it to reflect how I feel about and conceptualize these subjects. And these three things together mean that I often come across this problem. Take this up here, for example. Four-dimensional n=4 supersymmetric quantum field theory. How do you draw that? What do you put on a page? So this brings me to a question which I feel like a lot of you probably have to grapple with yourself, which is very broad. How do I visualize things that don't fit on a page? Now, this is unanswerable, of course, but I'm going to break down a few regimes in which I can, at least say what I've attempted to do. And the first one is a literal one, which is I'm a geometer. I like spaces. I like high-dimensional spaces, manifolds. How do I draw a high-dimensional manifold on a two-dimensional page? And then there's this more abstract question, which is I often need to represent a mathematical abstraction, need to make it so you can relate to it. How do you put a face on a mathematical abstraction? And these two are about individual ideas. Then there's this more global question. How do I represent how the ideas fit together? It's almost a cartographic problem. How do I map the landscape of an entire field of math? Still fairly unanswerable, but again, I can tell you some of the methods that I have used. And to preempt my preclusion for rambling, I'm going to do this in a nice, digestible list format. So here's an alternate title for the talk. Top 9 tips and tricks for drawing mathematical and pedagogical ideas with emotional content. Number 6 will shock you. Thank you, Leonard Euler. All right, let's get into this. I'm going to start with this literal question. Drawing high-dimensional manifolds. And the natural place to start is which manifolds is this already a solved problem for? Which ones can we actually draw? And, there's some that already have some pre-existing shorthand in diagram. Right? So here is, for example, a vector space. I started by drawing R3 with those 3 little axes, and then I just kept drawing more and more and more axes, and then put a little n on top of that. So then it's Rn, n-dimensional space. And it kind of feels like I'm cheating. But honestly, this works pretty well because our mental model of 3-dimensional space extends reasonably well to higher dimensions. It's still going to be flat. You will still be able to add points together. And things that we can make easily from Rn are still reasonably representable. Take, for example, an n-sphere. I'm just going to draw a normal 2-sphere and then put an n next to it. I'm going to leave you to do the rest. Or maybe an n-torus. I mean, a torus is made by taking flat space and making it periodic. So we just draw the 2-dimensional version, put an n on top, you get the idea. Now, I think about these free spaces as sort of the Lego pieces, the building blocks that most other things can be made out of. And I feel like I end up drawing these a whole lot, like especially the tori. I draw so many tori. In fact, tip number 1, learn how to draw a torus because it comes up again and again and again and again and again. Okay, what about something that's a little bit more complicated than a torus? Well, tip number 2 is to slice things up. I mean, this is a very natural way to represent and visualize a high-dimensional space. I just take cross sections of the space that are low enough dimensional that I can visualize them. It's like an MRI machine. You can see little slices of your brain, you know? So I just need to represent the low dimensional slices and then give you the tools to show you how they fit together and then let your brain do the rest. Take, for example, this tangent bundle. I start with a 2-dimensional manifold, and at every point, I'm going to include the space of all of the vectors that are tangent to the manifold at that point. 2 dimensions of manifolds, 2 dimensions of vectors, 4-dimensional total. 4 dimensions is already more than we can represent, but I can represent it by slicing up that vertical direction. So the slices in this case are going to be these 2-dimensional vector spaces. 2 dimensions is lower enough that we can draw it precisely. And next, I need to show how they fit together. And that's what this base manifold is showing. It's showing you one 2-dimensional vector space for everything along this lower dimensional space here. Okay. That's reasonably standard. Let's do something a bit more fancy with this. This is actually a very flexible approach. So here's an example of a space coming from string theory. Oh. And the slices here are 4-dimensional hyperboloids. In 3 dimensions, a hyperboloid is found by taking a hyperbola, spinning it around, and there's this kind of like circular neck in the center. In 4 dimensions, that circular neck is replaced with a spherical one. And that's the one that I'm drawing right there in the center. So I have the slices, but this time the slices actually change shape as I move around. And I need to tell you how they fit together. And that's what those 2 blue lines are for, because the distance between those 2 blue lines tells you the radius of that central neck. And when those blue lines cross, that central neck squeezes and squeezes and squeezes into a single point. And then your hyperbola becomes a singular hyperbola, which is a cone. And we see that these slicing it's not frivolous. It's mathematically significant. Even in string theory, this is how we understand the space. And it makes sense that the same tools would be used for both mathematics and its visualizations, because both of these seek to understand the object at hand. You just do it in slightly different ways. Here's an even stronger example. This is a picture of RP infinity, the infinite real projective plane. A little bit of history. I actually drew this at the PCMI summer school in illustrating math like 3 years ago, where I met many of you and where the Discord server that we're all talking about this on was made. Anyway, how did I make this space? So it starts all the way at the bottom with a single point, a 0-dimensional object. And then that 0-dimensional object gets extended to a line, and then I attach a circle to it. Okay, that's 1 dimension. And then I extend that circle up, and then I attach a 2-dimensional disk to this. And I do it so that the boundary wraps around twice. Okay, take that space, move it all up. And then I get a higher dimension. I attach a 3-dimensional disk where I wrap the boundary around twice, and again, and again, and again. I keep climbing the ladder of higher and higher dimensions. So this at the bottom is quite a literal slicing technique, not slicing in the exact form of cross sections, but in the sense of decomposing the space that I don't understand into simpler spaces that I do and explaining how those spaces fit together. And in fact, mathematically, this is exactly how we understand RP infinity. This is called the cell decomposition structure. But as I go up, you know, my slices become too untenable. Already in 3D, it's hard to see. How would I do higher? So I switch to a more interpretive way of going about it. I show this RP infinity sort of disappearing into the haze of infinite dimensions, this edifice leaning over you. Now it's more about the emotional content rather than the literal one. And this is interesting because it shows that like each of your parts of your image don't have to be doing the same thing. In fact, we can do tip number 3, slice things up semantically. If you think about it, mathematical objects contain vast multitudes of information. There's so many ways to look at it. All of them you want to communicate. But if you try putting them all in the same picture, all at the same time, it's illegible. In my experience, you can only represent 1, maybe 2 things at once. So we have this issue. How do we take the high dimensional space of all the things we want to illustrate about this object and project it down to the 1 or 2 dimensional, you know, space of things we can legibly do? That's the exact same problem as before. And the answer is the same. You slice it up. You take different semantic cross sections. In other words, you spatially separate and have different pictures that all show different, visualize different data about your mathematical object. As an example, over here we have this space that I quite like, which is called the Hitchin moduli space. And right now I've drawn it as just a smoke monster. It's nebulous. She's a little bit mysterious. But she's a smoke monster because really she's a shapeshifter, and she takes many forms. So as an algebraic variety over here, we see that I drew her in a way to emphasize the singularity structure right here in the middle, the structure that is apparent from an algebraic variety. You can also think about her as an analytic manifold, in which case there's a natural function on her, and I've represented that as this height. I'm showing different data for each of these pictures. And over here we have a fibration structure. Another way of looking at her, she has slices above a flat base where each of the fibers are going to be different toruses. And as you move around, some of those toruses pinch off. That's what we're seeing here. And you'll notice tip number 1, tori are coming up again. And tip number 2, I'm using slicing to represent this literal picture. So all of these things come together to show lots of data about this space in a legible way. So far, I think this is good for these literal interpretations, and I think of these as sort of the bread and butter. Like oftentimes as I'm doing more abstract things, I'll always go back to trying to do things literally, and you'll see these things coming up again and again and again. But now we're going to move to the second, more abstract regime, which is the question of how do we put a face on an abstraction? And the first tip is tip number 4, to add eyes, to just do it. Put a face on something, you know? This is very powerful because it lets us anthropomorphize things. And when we anthropomorphize things, we hijack humans' understanding of emotional and social dynamics. And we can use that to explain the math. And it's also powerful because it provides an extra layer of emotional interpretation, from the symbols on the page to how you should feel and like interact with these objects. So here's my Hitchin moduli space again in this algebraic variety picture with this singular point at the center. And you see that she's scary. She has big teeth. Not something you really want to work with. But in the field, there's something called this desingularized version of this space. And there we basically cut out all of those bad points, the points we don't like, and we get something that's much, much easier to work with. And we see that now she's smiling, you know, she's friendly. Someone you want to work with, you know? We are seeing this, like the metadata of how we should be engaging with these objects represented visually based off of the emotions that they're conveying. And also just like, I mean, look at those eyes. How could you say no to those eyes? Now there's a fundamental issue to this, which is, what do I draw the eyes on? I mean, it kind of doesn't matter. This one is just a literal ball of smoke. But there's so much freedom in how you represent an abstract idea. How do you choose which one? What do you even pick? And what I like to do is I like to use puns. So here's an example of another space. This is the moduli space of G bundles, where G is a group. It's quite related to the last space, actually. Generally, people write this as bun sub G, G bundles, bun G. So I drew her as bun G the bunny. And some tips here. First, first tip is that we add eyes to this thing, make it cute. Second tip is we draw her as a torus because in some cases she is quite literally a higher dimensional torus. And third, there's some semantic slicing going on. I mean, Bungie is an interesting space because she wears many hats. There's many different geometric structures on top of her. First, there is this symplectic structure all the way at the bottom, that first hat. And then on top of that, there's a line bundle, this little straw hat shown by these little pieces of straw. And then on top of that, there's a complex structure. Now, if I tried to represent these all literally everywhere on Bungie, it would be unreadable. 3 things at once is too much. But I separated them hat by hat by hat, stacked them on top of each other. Here's a more interpretive version of the same thing. This is a picture of a symplectic structure. A symplectic structure is a sort of geometric thing on a manifold. It takes in two vectors, it eats them, and it spits out a measurement of a sort of area. So you see this little guy is holding two vectors, and it's spitting out this parallelogram, which represents the area. And why did I draw it like this? Well, because the symplectic structure, like you see over here, is usually denoted by omega. So I drew it just as an omega, you know? And then now that I have a form to it, I can do tip number 4, add eyes, make it cute. Okay, I like puns, so I'm going to do some speed runs through the puns. This is a picture of a spectral curve, realized quite literally as a curve that is a specter. And you'll see that the eyes of this curve are symbolized by an equation, which is the defining equation of the curve. Okay, here is a picture of the Hitchin moduli space from earlier and its mirror symmetry, realized as it looking through a literal mirror. More than that, I'm proud of this one. SYZ mirror symmetry is the specific type of mirror symmetry that's going on. And the letters SYZ are themselves mirror symmetric. The S and the Z are flipped and the Y is symmetric around the axis, which means it makes for quite a good mirror decal at the top. Now, this mirror symmetry as a pun, like the fact that I'm representing it with a mirror is hardly a pun because that's just in the way that mathematicians already think about things. And this is quite interesting. Hello, giving a talk. This is interesting, and it comes up in different places too. So here is a picture of Gromov-Witten invariants. So Gromov-Witten invariants are something you measure on a symplectic manifold by counting the number of holomorphic curves sitting inside. Holomorphic curves are these bad boys here. All of these things are holomorphic curves. And to symbolize that, I have Gromov and Witten doing their survey trip and literally counting all the little holomorphic curves. And I'll just point out a couple things, like there is, again, a lot of slicing going on to show this progression of these bubbles and a lot of tori that I'm drawing. Everything comes back to those bread and butter literal drawing tips. Okay, now I want to get more into the nitty-gritty about how I actually, put the ideas onto the page. And to do this, we have tip number 6, which is to build a set of coherent visual rules that your image will follow, which is useful because it makes things readable and it makes things aesthetically consistent, and we love aesthetic consistency. But more to the point is that these visual similarities can communicate semantic relationships between the mathematical objects that are hard to see otherwise. And doing so, we're hijacking our human visual cortex for seeing visual relationships and turning those into mathematical relationships. So here is the sort of most standard form of this idea, which is color coding objects. And the picture that I'm using, this is a picture from a paper that I wrote. In this first thing, you have this sort of crystal lattice, which then transforms via some transformation. It turns into the structure in part B, which I then put on a torus and get the structure in part C. So let's go through this and see what the visual rules underlying this are. First off, there's always this blue background. So we understand that the blue represents the substrate on which the interesting things are lying on. Second, we see that there's these white dots that are the same style everywhere in A, B, and C, and that communicates that it's actually the same white dots. These two dots in the center of the cell become these two dots in the diagram with arrows, and become these two dots when you put them on a torus. And finally, the yellow connections that look like bonds between things in a crystal, those become the yellow connections in part B, which are now arrows between these nodes, and they become the arrows in part C. This is all extremely efficiently communicated by the fact that I have a consistent visual language. So let me give a more interesting example. Tip number 1, draw some tori, still here. More interesting example is, this is a picture I drew of symplectic reduction, which describes what happens when I take a symplectic manifold and I have a group acting on it. You should think about this by like rotating the manifold. And when you do this, it decomposes in a very interesting and, explicit way according to the different orbits of that group, according to the different ways that different parts that rotate into each other. So there's a lot going on here, but I want to stress, like I am doing quite a lot of slicing here in my visualizations. You see this This cone right here is a slice, and this is, in fact, the literal slice that the mathematical, theory of symplectic reduction spits out. Again, mathematical and visual slicing are the same. Again, also some tori. Can't forget tip number 1. But what I want to focus on is the brush design of one specific brush in this picture, which is specifically this black calligraphic ink brush. You see it up here going on, you see it around here, spinning around, and we see it at the bottom. Now, everywhere in the picture, this black ink represents the group action. And that tells you, just by looking at it, that whatever is going on up here is the same as whatever is going on down here, even though they're visually separated. And in particular, this brush is a very kinetic brush. It has a lot of motion. It draws your eyes along, and the ink splashes fly off from the side, and it suggests a lot of motion. Because this is not a static image, this is a dynamic one, and it represents the underlying dynamicism of the group acting on the manifold. The group's action is the motion of the ink brush. Okay, I'm going to peel back the curtain even more and talk about how I got this effect. So I do all of these drawings in an app called Procreate on the iPad. It's a very nice learning curve. It's only $10. I recommend it. And here is the process for getting this ink brush. Yes. So what I do is I pick my brush here. I'm going to start with this watercolor brush I designed and give it a little background. And then I'm going to go to the ink brush. And I'm going to switch my color at the top. I'm going to turn it black. And I'm going to write my own name in cursive. Yes, my name. And you'll see that as it's going, in the faster parts where I'm turning quickly, the inks fly off. Right? And this is because I actually have 2 brushes, one on top of the other. And the calligraphic brush, which is what came with the program, I designed that to follow the pen more closely than the splotches behind. So during fast motions, they separate, and it gives the illusion of a physical pen going across the paper, flinging ink off of it. So these visual tools are very useful for clarity in the sense described before, but there's also the emotional impact of them. Contrast in visual design gives you contrast in vibes. Like take this is an example of me trying out a few different visual designs that I wanted to use. And up here, first off, I'll note lots of tori again. Up here, you can imagine this sort of ethereal donut has a very different feeling to it than this splotchy pastel watercolor one. And you can imagine how that can be used for great effect, for having different mathematical objects give you different emotional responses. In particular, there's a bit of this isn't just purely visual, there's some cultural component to this. I mean, pastels and watercolor, they communicate children's drawings and picture books. And that's part of what gives them this emotional resonance in your head. And in fact, this connection with culture is also a very powerful tool in this, which leads me to tip number 7, which is to use cliches liberally. A cliche, I'm thinking of this as just cultural shorthand, an analogy relating the mathematical objects I'm trying to describe to some cultural reference that the audience understands. And it's a very efficient way to communicate lots of data. Essentially, we are hijacking humans' cultural understandings to become mathematical understandings. So here's an example from not me. This is called the principle of the symplectic camel. This is another name for a theorem in symplectic geometry called Gromov's non-squeezing theorem. It states that if I have a symplectic ball and I squish it and squash it however I can, if I do so in a symplectic way, I can never fit it through a hole if that hole is smaller, has a radius smaller than that of the original ball. Now, this was popularized by science writer Ian Stewart with the saying, "You can't fit a symplectic camel through the eye of a needle, the principle of the symplectic camel." And here is my drawing of this, showing a symplectic camel trying its darndest to fit through a needle, but it can't because its big fat hump is too large area for the area of the needle, shown by those blue cross sections. Tip number 4, add eyes. Now, this is a common saying, and it goes back to the original cliche, which is the Bible. It is easier for a camel to go through the eye of a needle than for a rich person to enter the kingdom of God. It's a very evocative phrase, and it gives you some very evocative math. Now, one cliche that I'm particularly apt for is storybook aesthetics. I think of math as storytelling, and when I tell math, I am telling it as a story, and I want my readers to engage with it as such. So for one presentation I did, which I'm showing a slide from now, I took that to the logical extreme, and I had my actual slides of the presentation be pages of some bedaggered book. And then the page flipping, the slide change animation was like a flipping of the pages through. It was very cute. But the particular style of book I was going through here was this sort of young adult fantasy book exemplified by The Hobbit. Now, as a kid, I loved, when I was reading The Hobbit, I loved flipping to the back and seeing this, multi-fold map of Middle-earth. And on the left, you'd have the Shire where they all started out. And then all the way on the right, you'd have like the lonely mountain sitting alone, and smog circling around it. And you just knew that that's where they were going. And what I did here is I did my own mathematical version of that drawing with this place where they're starting here all the way to this, final boss on the right. So this is a picture of this land of integrable systems. And you can kind of see the journey very efficiently described in this map. They start in this gauge-theory growth. They kind of meander along through Louisville's theorem, symbolized as Louisville, the city. Tip number 5, use some puns. And then, crossing the mountains, trudging through the Soliton swamp, and then braving the spectral cemetery until they can finally face off against the Cyberquitten summit. What's happening is that this map tells you not just that, it doesn't just make you think of fantasy and adventure, it also codifies the hero's journey in this mathematical journey. You know that as you go along, each of these little named places will be detours that you stop off at, stories in their own right that have a beginning and end, but still all build together for this final confrontation at the Cyberquitten summit. It's very efficient. And this is what has happened when they actually reach to the summit. This here is sort of the audience stand-in. It's a picture of a physicist looking evil as always. And this is sort of this scary nilpotent cone. Now, I actually drew this in quite a literal way, and I used the tricks from before. For example, tip number 1, I used all 3 of those building block spaces. I have this vector space at the bottom. I have these tori fibers sliced up nicely. And at the central slice, I have something composed out of spheres. But more to the point is that this is reminiscent of like a castle on the hill in a dark and stormy night. And you see this flash of lightning and the castle stands in silhouette. And what happens in the story when you see the castle in the stormy night? You go inside. You try to solve the mystery. You try to face whatever demon is in there. And somehow you know that that is where the resolution of your story has to lie. This is the thing you have to conquer. This cultural shorthand gives a lot of metatextual analysis, framing how we should see the objects in my mathematical story and how they relate to each other. So far, we've done everything with representing single ideas and how to represent those better. And I want to move on to this question of how we connect those ideas to each other and how to use, how to build those connections. And tip number 8 is to use real-world hierarchies. So the real world is full of things related to each other, like the roots of a tree support the tree. The tree grows from the roots, for example. And what we want to do is we want to establish an analogy between mathematical objects and real world objects so that these real world relationships tell us about the mathematical relationships. Essentially, we are hijacking our human understanding of the real world to become mathematical understanding. So this example here is one of a Lie group and a Lie algebra. And the way I encoded this is that the group is represented by the tree, while the algebra is the roots. And this makes sense because you take your algebra and then you flow along it, and this is what makes the group. It comes from the algebra. And in this drawing, I'll point out that I'm doing some semantic slicing here, in the sense that the algebra is being represented in different ways. Here it's being represented as a flat space, and here it's being represented as a flow along the group. Those would be messy if they happen at the same time, but I move them apart spatially. And this is so effective because I use tip 6. I'm using these visual rules that the root type things are always going to be the algebra to communicate that it's the same structure here and here. Okay, let's give a more in-depth example of this. So I'm going to describe a relationship between symplectic geometry, which is on the left, and contact geometry on the right. So symplectic geometry is, it lives on a even dimensional, say a 4-dimensional thing, and it's going to be represented by these little critters, these symplectic forms that I showed you a picture of earlier. And on the boundary of that 4-dimensional manifold, these become contact structures, which here are represented by these planes that are twisting along. And I'll just note a couple tricks. I'm using slicing, so I'm only showing some of those planes at a time, and I'm letting you fill in the rest. And I am communicating that the symplectic structure becomes the contact structure just with this visual language that these are the only red things in the picture. It's color coding. But the point that I want to make is I have the relationship between the mathematical objects that one lives on the boundary of the other. When does that happen in real life? Well, the cliff face is the boundary of the cliff. So I put contact geometry on the cliff face and symplectic geometry on the full body of the cliff, and that communicates the relationship. There's some more going on. For example, in mathematics, we think, at least I think about geometric structures as living on top of an immutable manifold and moving around on it. The way I represent that is the symplectic forms are themselves critters that live on top of the manifold. And tip number 4, they're critters because they have eyes and it humanizes them. It makes them, things that we get to play with. And the specific thing I'm trying to show in this picture is called Darboux theorem. As a brief summary, it says that you can always find a way to look at your manifold such that the symplectic form becomes flat. Now, how do I represent a flat structure? With scaffolding. Because what is scaffolding in the real world if not a way to turn a curved ground into a flat surface, a flat structure on top of a curved manifold? So we have all of these ideas together. We have all of these tips. Now it's time to put them together. And I'm going to do a bit of a case study, which is that of the mirror symmetry. This is the picture I teased you all the way at the beginning. So fundamentally, it all starts with a flowchart. Here's actually the original flowchart of that picture on the left. On the right, you can see it looks very different in this form, but a lot of the mathematical content is still there. And what I'm trying to do in this flowchart, or this picture, is to explain the structures and the relationships between various types of quantum field theories. What those are doesn't really matter. These are the structures I'm working with. Now, all of these field theories are related by a process called mirror symmetry. And in this flowchart here, that's exactly this vertical line. Everything on the left has a mirror thing on the right. So the way I envision this is with this grand mirror symmetry. Tip number 5, use some puns. So let me show you this underlying structure. And we're going to do this by exploiting real-world hierarchies. A tree is supported by its trunk. The trunk is the most important part where everything comes off of. And at the top of this trunk, we have this fundamental starting theory, 4D, n equals 4, supersymmetric angles, whatever that is. But the point is, this theory descends down. And as it goes down, it induces all of the theories below it. And the way it does that specifically is through a boundary. You see, this is a 4-dimensional theory because I drew this little hypercube in the background. And as it extends downwards, it hits a wall. It falls off the side and it ends on a three-dimensional boundary. And on this lives a three-dimensional theory. Okay, and then the trunk keeps going down, and this three-dimensional part of the trunk ends on a two-dimensional surface with an associated two-dimensional theory. And that two-dimensional surface descends down until it ends on a single line of wood, a one-dimensional theory. And this wood turns into the roots and spirals around until it ends up all the way at a single point, 0 dimensions. Every theory is induced from the one above it as a boundary theory. Okay, what's next? What's next is we add the branches. So mirror symmetry relates two different modifications you can do to a theory, one called an A twist, one called a B twist, but these are always going to be represented by branches of this theory, one over here, one over here. And mirror symmetry is exactly the relationship between these branches. This is the bilateral symmetry that bifurcates my entire tree. And I was very careful, you'll see, to have different aesthetic considerations for the different sides. The B twist and the mathematical structures you get therein are a lot nicer to work with. It's smooth. It almost flows together. Whereas the A twist and those mathematical structures are somewhat hairier. So it feels like it's, I don't know, Halloween or something. So in order to build this mathematical contrast, I used visual contrast. Tip number 6, build visual rules. And then this sort of descends down. These two branches get mapped down layer by layer by layer. Every theory, every layer of the tree has its own two branches that are still related by mirror symmetry. And in fact, in 3 dimensions, these two branches, one of these, this one over here, is called the Coulomb branch. One of these is called the Higgs branch by physicists. So, you know, it makes a lot of sense to realize them as actual branches of the tree. Tip number 5, use puns. Okay. Now we add the foliage. What lives on this branch? Well, mathematically, what I want to represent is that each of these two twists are give me maps from my sort of trunk space area, this three-dimensional thing in this layer, into some other manifold. I don't know what that is, but the way I'm going to represent that is I'm going to turn that other manifold into a bunch of leaves. This collection of leaves is the target. And this is, you know, useful because what, like a branch, it exactly is something that carries the trunk to the leaves. You know, makes sense. And I've stylized the leaves differently still too, because one of these, this B side, the happier one, is sort of this spring colors, while the other side is more autumnal. And this is using the cliche that spring and autumn are often separated as like dual seasons to one another. And I'm using that duality to represent the duality between the two sides of the tree picture. I'm using a cliche. Tip number 7. Okay, one more structure inside of this. We see that, like, in mathematically speaking, each of these manifolds appears multiple times. So this one here actually appears inside of the one layer above it as what's called a boundary condition. And in the tree, the way I represented that is I had this sort of fungal rules where the fungi stretch from this manifold here and embed into this upper one. So, and also on different sides, I'm using different pictures, different ways of realizing this fungus. But the point is, I'm manifesting this space differently in different parts of the image. This is semantic slicing. Tip number 3. And here's one more hierarchy. There's another operation I can do, dimensional reduction, which mathematically and physically both are shadows. They are projections onto something that lose some amount of information, but still follow the structure of the thing up top. And finally, I need to add eyes, the little critters. What's living in this tree? So here's an example of some little acorn critters that are living inside that are representing monopoles. And then you see that they start in three-dimensional space, and these get mapped all over the place and are very useful in the theory. What I'm drawing here is that they start growing on 3 dimensions, and then they fall down and get projected onto the 2-dimensional branch down there. So add, there's some, alive element here. So here's what we've got so far. We have this whole structure, and we've used all of these rhetorical tricks that I've built up so far. You know, we're hacking into our visual cortex, our physical understanding of the world, our emotional relationship with things with eyes, and cultural shorthand, all used to analogize and help us better explain and connect with mathematics. But it feels like it's missing something. And this brings me to tip number 9, which is to give this life. There's a term called a Wimmelbilder, which is a name for a large image teeming with figures. Now, one canonical example of this is Where's Waldo? You could get lost in this forever trying to find the sneaky little guy. But one that's more attractive to me is these geologic diagrams. These are more of a direct inspiration. As a kid, I loved these. Could get lost watching the arrows, following the arrows all along. There's almost dioramas of what's going on in the real world around me, but it's on a page. It's so cool. And math to me is a world. And what's so great about it is that I get to manifest it. I get to make the diagrams that show how it relates. I get to build my own worlds inside of math. That's why I love it. So it means that I can't just start with the ideas and with arrows connecting them. I really need to show the framework around it. I need to give it colors. I need to give it a background. I need to give it leaves. I need to give it shadows and saturation, and I need to make it pop. And most importantly of all, I need the sunbeams, because for me, math glows. Thank you. That's all I have.
All right. Thank you very much, Elliot, for that lovely explication of your wonderfully original ideas. We have reached the top of the hour, and so what I'd like to do is refer questions to the Discord channel, where there's of course, a seminar channel. And I'd like to adjourn this meeting. Thank you all again for coming, and I hope to see you next time. I will stop the recording.